I gave a version of this talk online a couple of months ago, so I will try to follow the same outline, adapting it as we go. So let me try to first give an overview what this lecture will be about. So the title is Additive and Multiplicative Hankel and Toeplitz operators. So the aim of my talk is to consider the following diagram. Okay, so let's start with Toeplitz. What are Toeplitz operators? Toeplitz matrices are infinite matrices of this form. Okay, these are Toeplitz matrices. So Hankel matrices are infinite matrices of this form. Okay, so roughly speaking, for a Toeplitz matrix, we have constant elements lying on such lines, and for Hankel matrices, we have constant elements lying on these lines. Okay, so they are very different classes, but nevertheless there is some kind of affinity between them. It's a bit like, you know, Toeplitz and Hankel, it's a bit like Marx and Engels. You know, they're usually mentioned in the same sentence. So it's usually convenient to consider them both. Now there are also multiplicative Toeplitz and multiplicative Hankel. So multiplicative Toeplitz are matrices of the following form. You have, so I will use different notation here, N and M. Okay, so, sorry, should be N over M. And here, Hankel, N times M. Okay, so what are the differences? So instead of adding, I use multiplication. Instead of subtraction, I use division. And of course, I don't want to divide by 0, and so I start from 1 rather than from 0, my indices. And it will be convenient to just distinguish. So notationally, J and K will be integers starting from 0, and N and M are integers starting from 1. So we have this table, this kind of diagram. Okay, at the first sight, when you look this, you think, what a weird thing to do. This is completely unnatural. This is just, you know, artificial construction. But I will try to convince you that these two objects, they have the right to exist, and they have some natural pedigree going back to the theory of Dirichlet series. Okay, so let me try to explain. So So let me make some public admission. So 5 years ago, I didn't know what the Dirichlet series was. Okay, so and mathematical physicists are not normally thinking of Dirichlet series. So let me just in case remind you what it is. So a power series as everyone knows, are series of this form, and Dirichlet series are series of this form. Okay, so here we denote the variable standardly by Z, complex variable. The tradition here in the theory of Dirichlet series is to denote the variable by S. This tradition goes back to Riemann, so who we are to dispute this? I will stick to this notation. S is a complex variable. So Toeplitz operators and Hankel operators, I will explain how they arise naturally in the theory of Hardy spaces. So Hardy spaces are spaces built from this power series. So basically you take such power series and you impose the right norm, the right Hilbert space structure, and you get a Hardy space. In the same way, if you start from Dirichlet series and impose the right function space structure, in fact the Hilbert space structure, you get a certain function space which is interesting enough and which has started attracting the interest of analysts from late 90s, I would say. And we will see that these matrices, these infinite matrices, can be considered as matrices of certain operators acting naturally on these spaces of Dirichlet series. Okay, so this is the idea. My aim is just to introduce basically these objects. So today I will be mostly speaking about the first part of this diagram, just reminding you the key facts of the classical theory of Toeplitz and Hankel matrices and operators. And then next time I will move on to the second line and we'll try to explain talk about these multiplicative objects. So necessarily because of the restriction of time, it will be very sketchy. So the topics I will try to address will be the following. So I will talk about the realization of these operators, of these matrices as operators in function spaces. Function spaces. I will talk a little bit about boundedness. So, you know, when you see a new class of operators, one of the first questions you ask, is it bounded, or and so on. Then I will talk about just some beginnings of spectral theory. Some very basics, and maybe, if I have time, a little bit about truncations. Truncations. So truncations are, for example, for a Toeplitz matrix, you may consider not the full Toeplitz matrix, but you know, the top left corner of it. So these are truncations. And it makes sense to ask about truncations for all of these classes of functions. Okay, so that's the aim. So let me start with additive operators. Additive Toeplitz and Hankel operators. Some definitions and examples. So, by the way, for experts, there will be nothing new definitely today, nothing new at all. So today I will be just talking about the first line of this diagram, as I said. Let's fix a function phi. We will call it a symbol. Function phi in L infinity on the unit circle, and I will write it. I will write its Fourier expansion. In this standard form. So phi hat are the Fourier coefficients. So then corresponding to this function, so z is the variable on the unit circle. So corresponding to this function, we associate with this function two infinite matrices, a Toeplitz matrix and a Hankel matrix. So T of phi will be phi hat of j minus k, jk from 0 to infinity, and Hankel of phi will be phi hat of j plus k, jk between 0 and infinity. So now now I claim that these infinite matrices are in fact matrices of some operators acting on a suitable function space. So let's first recall what is this function space. It will be the Hardy space. And let's see how to define these operators on this function space. Okay, let me see if I can swap it. Yeah, okay. So let me recall the definition of the Hardy space. So the Hardy space on the unit circle, this is the set of all series of this form where the coefficients belong to little L2 space. Okay? And so, of course, we have a Hilbert structure on this space. This is a Hilbert space. This is a Hilbert space, and it's naturally embedded into the corresponding L2 space. And we have the corresponding natural projection. Some people call it Rees projection, some call it Hardy projection, some call it Zeger projection. So this is P, which takes a function defined by the series where the coefficients go, where the indices go from minus infinity to infinity, and it just kills the negative part of this series. Okay, so we just kill the coefficients with negative j. Okay, so this is the natural orthogonal projection. Okay, so yeah, and the good thing about Hardy space is that we can think about it in three different ways, in fact. So one way is to think about its Hilbert structure as given by the set of coefficients here. That's fine, that's okay. So that gives us a natural isomorphism with little L2. Another way is to think of it as a subset, subspace of a function on the unit circle. That's also very useful. And the third way is to think of this Z as being not on the unit circle, but inside the unit disk. Then you get an analytic function. And all of these three ways are useful. Okay, so it's like a bit Okay, so I'm trying to appeal to mathematical physics intuition. When you think of Schrödinger operator, sometimes you want to think about coordinate representation, sometimes about momentum representation. So the same way is here. Different pictures are useful. Okay, so now we have all the definitions here. And so I want to define the two operators. So I will abuse notation a little bit, and I will use the same letters. You will understand why in a minute. So let me define operators T of phi from H2 to H2, right, from the hardest space to itself. Which is defined in this way. So let me write down now the Hankel, and then I will explain the notation. Okay, so let's first deal with Toeplitz. So we take a function from the Hardy class, okay, and then we multiply it by the symbol. So note that f is analytic, right? So it depends by, when I say analytic, I mean that it has no coefficients with negative indices in its expansion. But then I multiply it by phi, and this phi doesn't have to be analytic. So the analytic and anti-analytic parts here get jumbled up after multiplication. But then I project back onto the analytic subspace. So in some sense, we can say that this is a compression of multiplication operator onto the Hardy space. Okay? So that's the Toeplitz operator. And we will see in a second that actually this is the matrix of a Toeplitz operator in the standard basis. For Hankel operator, we do the same except for some twist. So when I take my element in the Hardy class, I actually flip it, and I started with Z, and now I consider Z bar. So when I write Z bar, I mean Z being on the unit circle. So Z bar, of course, on the unit circle, Z bar is the same as 1 over Z, right?
When we read Z bar instead of 1 over Z. 1 over Z is analytic.
No, but so when we are on the unit circle, right, not on the unit disk, yeah. This is why it's convenient to write it in this way. And so Z bar to the J, of course, is the same as Z to the minus J. It's the same thing. Okay.
So therefore, Z bar is not in H2.
Not in H2, exactly. It's not in H2, so, but it's still in L2. Okay, so it's anti-analytic. Okay, except for constant term, but let's not worry about the constant term. Then I multiply it again by this symbol phi, which doesn't have to be analytic or anti-analytic. And again, the coefficients get mixed up. Analytic and anti-analytic part gets mixed up. And then I project back onto the analytic component. Okay? So intuitively speaking, what happens is that if you take the multiplication operator, so heuristics, if I take the multiplication operator, multiplication by phi in L2, right? Then its matrix in the standard basis is just a convolution matrix, right? So its matrix is just a convolution matrix. So I have constant elements here. Okay, but when I split L2, into the analytic and anti-analytic part, right, then here, let me get another color. Okay, here I get Toeplitz, right, and here I get Hankel, something like this. Okay, this is heuristics. You have to make it a little bit more precise, but roughly speaking, that's what's going on. Okay, now let's make it slightly more precise. So let's just compute. Let's just take, for example, the Toeplitz operator and compute its matrix in the standard basis. I claim that it's going to be exactly this. This is the only computation I'm going to do in the lecture, so let's do it. All right. So for Toeplitz operator, I take Zj, Zk. So this becomes projection of phi multiplied by Zj, comma Zk. Now Zk is already analytic because k is positive. So if I can move this p to the other part, but then I remove it. I remove it because p of Zk is Zk. Zk is already analytic. So I end up with phi dot Zj, comma Zk. And this is in the product in L2. Okay, this inner product is in L2. So then I can move this Zj to the other part because we are on the unit circle. So I get phi Zk times Zj bar. Inner product, скалярное произведение, inner product. And so now, because, as I said here, right, putting bar is over this z is the same as taking 1 over z. So what I end up with, phi z k minus j, and this is precisely the Fourier coefficient of j minus k. So I think it should be k minus j here rather than j minus k. So I've mixed it up, but otherwise it's correct. Okay, so k minus j. So if I do the same calculation with Hankel now, what changes? Okay, so let me just edit this line, right? So if I do the same calculation with Hankel, what changes here is I have to put bar over this Zj because of my definition of Hankel. Okay, so I get this bar over Zj. And so when I move it to the other side, this bar disappears because I apply bar twice. And so instead of k minus j, here I get k plus j, and so this is k plus j. So this is the calculation. And so we see that the matrix, that indeed these two operators acting on the function space, these are operators whose infinite matrices in the canonical basis of the Hardy space are precisely those two elements. So just to give you a little hint, a little preview of what comes next, with this calculation, when we multiply powers of z, when we multiply zj and zk, the powers get added up, right? Imagine that you take a Dirichlet series and start multiplying two Dirichlet series, right? You get n to the s somewhere and then m to the s somewhere. When you multiply them, n and m gets multiplied rather than adding up, right? This is the kind of the hint of why the additive structure becomes multiplicative structure when you try to transport this theory to the set of Dirichlet series. Okay, but we will discuss this next time. All right, so this is the definition. Now I want to just maybe give a couple of examples so that this is becomes slightly more concrete. Oh yeah, one thing before I move on to examples is one little remark. Is that the Hankel operator depends only on the analytic part of phi, right? Look, so the Hankel operator, the Hankel matrix, so you can just look here. It really depends only on the Fourier coefficients of phi with non-negative indices. So it doesn't care. So I can, in principle, I can start with any function and I can add whatever you like for negative Fourier coefficients. But when you take the Hankel operator, it will not notice this. Okay, so this is just a little remark. Now let me go back to examples. Example 1. So I will mix Hankel and Toeplitz in my examples. So consider phi to be analytic. So let phi be in H infinity. So H infinity is, there are several definitions. One of them is the intersection of H2 and L infinity. So it's a bounded function which is also analytic. Okay, so it's a function of the unit circle whose Fourier coefficients with negative indices vanish. Okay, so in this case, the Tuplets operator is just multiplication because I don't need to put the projection here, right? If I multiply two analytic functions, again I get an analytic function, so projection we don't need it. So it's really a multiplication operator. Another example, yeah, in particular, if phi of z equals z, then the corresponding Tuplets operator is just what is called the shift operator. Okay, it just shifts the coefficient. It's multiplication by z in the Hardy space, so it's the same as shifting the coefficients to the right. If you write down your function and you look at its Fourier coefficients, the action of multiplication is the same as shifting all coefficients to the right and putting the first one to be 0. Example 2. So in the same spirit, if phi of z equals z bar, then this is just the conjugate of the previous guy. So this is what is called the backwards shift. Okay, so we take a function multiplied by z bar, so everything gets shifted to the left, but the constant in the constant term sticks out of the Hardy space, right? It becomes z bar, so we cut it away. Okay, so this is the backward shift. Okay, and last one for Hankel, the most classical one is the Hilbert matrix. So if we take for phi of z, this function, okay, on the unit circle, then the corresponding Hankel operator is the well-known Hilbert matrix. Okay, so this is just to sort of get us going. So now, what are the questions in this theory? So how should one think? Let's take a bird's eye view on these theories, the theory of Hankel and Toeplitz operators. So you should think of it as the study of the map from the symbol to the corresponding operator. So we are studying the properties of two maps. So phi is a functional parameter, and we look at the operator, and so it's the corresponding spectral properties. So like in the world of Schrödinger operators, for example, you start with the potential, and you ask for what potentials your operator is, I don't know, bounded, compact, and so on and so on and so on. So the same in this Hankel and Toeplitz world. You ask for what classes of symbols, you get the corresponding properties. So the typical questions you ask, is for what classes of symbols is your Toeplitz operator or your Hankel operator bounded, compact, trace class, etc., etc., etc. Right? Put your favorite property. So you want to describe the standard classes of operators in terms of their symbols. That's sort of one way of asking question. Another way of asking questions here is that what are the spectral properties of your Toeplitz operator or your Hankel operator for a concrete symbol. Of course, you cannot do this for all symbols, but if your symbol is from a reasonable class, for example, smooth, continuous, or something like this, you can try to describe the spectral properties of the corresponding operators. And another question which I will hopefully mention a little bit is the truncations. So what are the properties of the n by n truncations of the Toeplitz and Hankel operators. So you take the top left corner and ask what are the properties there. Okay. So this is the overview of where we are going. So now let me start with boundedness. Yeah, any questions before I move on? Because now I will start erasing this, so maybe while everything basics are still here, please feel free to ask. And then I'll go on to boundedness. Okay. So I'll keep the definitions here and I'll work on this board. So let's talk about boundedness. Okay, so let's start with Toeplitz. So for Toeplitz, the situation is very simple. Theorem. The Toeplitz operator is bounded if and only if the symbol is bounded, and the operator norm of the Toeplitz operator is exactly the L infinity norm of its symbol. Okay, so first of all, some comment. So you can ask me, well, we've actually started from a bounded symbol. So what do you mean when you say bounded if and only if the symbol is bounded? It's always bounded. Well, in fact, you can, in principle, define this operator for a wider class than the bounded phi. You can start from phi nil 2, for example, or even, from phi nil 2 would be good enough. And then you will discover that for the resulting operator, for the resulting densely defined operator to be bounded, you actually need to have an infinity property here. And of course, this equality with the norms, it kind of exemplifies it. So let me give a sketch of proof, or the idea of proof. So in one direction, this is entirely obvious. There is nothing there. So in one direction, in the estimate, in the upper bound here, right? So as usual, we split this into two bounds. So for the upper bound, there's nothing to do. We just look at the definition. We look at the definition. Of course, the projection is operator of norm 1, right? So we have this, and multiplication by phi has the norm equal to the L infinity norm of phi, and that's it. So the norm of f is the L2 norm of f, of course. So L2, like this. Okay. So in one direction, this is entirely obvious. In the opposite direction, let me just explain it by giving a picture rather than writing lots of formulas. So again, let me appeal to this multiplication operator. Okay, this multiplication operator in L2. So consider this multiplication operator. So multiplication operator in the full L2. Okay, so we do not project. Then if we write down its matrix in the canonical basis, in the basis of powers of Z, what do we get? We get this picture that I already had on the left board. Okay. And so now the actual Toeplitz operator is this corner of this matrix. Right? This is the Toeplitz operator. Of course, the norm of multiplication operator, as everybody knows, is exactly the L infinity norm of phi. Now, I say we're asking what is the norm of this corner, right? Of this corner of this matrix. But observe that, okay, I have this corner, but let me step back, okay? I make one step back in this direction, okay? What I get is exactly the same operator. It's unitarily equivalent to this operator. And then I can step back as well, again, and so on and so on. So these are unitarily equivalent copies of the Toeplitz operator. And they converge strongly to the full operator. Okay, so from this you can see that the norm of this corner cannot be actually smaller than the norm of the full operator from this argument. I don't want to write it down, but I hope intuitively this is clear. That's the proof. Okay, so we've got the norm. And so for the Toeplitz operator, the story with the boundedness and the norm is entirely simple. For Hankel operator, this is much more interesting. This is actually the beginning, the question of boundedness of Hankel operators. This is the beginning of the modern theory of Hankel operators. So let me discuss this. Okay, so let me start with an upper bound, which is true in the same way as it's true in the Toeplitz case. But before, let me remind you this remark that I had. So remember that Hankel operator with the symbol phi is the same as the Hankel operator with the symbol psi if phi and psi have the same analytic part. Right? Okay. And so now, if I look at the norm of the Hankel operator,
If and only.
if and only if, exactly, if and only if, thank you. Now if I look at the Hankel operator, its norm is bounded above, for the same trivial reasons, is bounded above by an infinity norm of its symbol. But then which symbol? There are many symbols, right? There are many symbols who have the same analytic part. And I can take any of them in this bound. And so I can optimize. I can take the smallest. So in fact, the more correct bound would be this. It is less than or equal to the infimum of the L infinity norm of psi such that P psi equals P phi. Okay? So this is the trivial norm bound combined with this remark that symbol is not unique. Now, and then the fundamental theorem due to Nihari is that actually this is not an estimate, this is an equality.
What is?
Equality. This is identity. It's not an less than or equal to, it's equal to. So this is the theorem. Nihari, I think it's 1957 or something like this. Nihari, yes, Nihari. N-E. Let me write it more. He was American-Israeli. I think he was born in America and lived in Israel. So Ziv Nihari, so he proved that in fact it is an equality. So we have an equality. So this should be not less than or equal, it should be equal. It should be equal. And of course, there is the corresponding statement of boundedness, which says that H of phi is bounded if and only if there exists a bounded symbol psi whose analytic part is the same as phi, the one we started from. Okay, so let me give a standard. I'm not going to prove it. It's not okay. It's not difficult, but I don't want to do it. Instead, I will give a simple example. I think I'll give this example, then we'll have a break. So the example is the Hilbert's matrix. Is it still here? Maybe. Maybe not? No. Okay, so I will reconstruct it here. So consider the Hilbert's matrix. This is the matrix, and we know this is one of the theorems we prove in the first functional analysis course, that this operator is bounded, right? This infinite matrix is bounded on little L2. And so we know that this Hankel operator is bounded. So what about the symbol and how does it agree with Nihari's theorem? So we can write down the symbol sort of naively in this way, okay? But we will notice that it's unbounded actually on the unit circle. Indeed, you see that as z tends to 1, we have a singularity. It's a logarithmic singularity. You can easily see it because when you put z equals to 1, this series diverges, right? So it has this series has logarithmic singularity on the unit circle. We actually can correct it a little bit. We can do the following. Okay, so what I'm doing here, let's say from 1, for example, I'm subtracting an anti-analytic part, right? The Hankel operator doesn't know about this anti-analytic part because it doesn't feel this anti-analytic part at all. But when you do this, when you do the subtraction, actually there will be some cancellations, right? So for example, at 1, okay, roughly speaking, you will have this cancellation of 2 series. And so in fact, this function is bounded, okay? So you can think of this guy as your phi you started from, okay? So you started from this naively, it's unbounded symbol, you've set up your operator, and the symbol is actually unbounded. From 0, yes. So 1 is simply because I'm allowed to subtract, I don't want to subtract constants because constants are still analytic. Yeah, but it's really nothing, you know. And this whole thing, right? This whole thing is psi. So this thing is already bounded. Okay, so psi is the bounded symbol of this operator. Okay, it's a very important example. Because of these cancellations. Okay, I don't do the exact analysis for you now, but if you group the terms here, you get z minus z bar j in each term. Okay, so you get this sign of j theta, and this sign will make sure that you converge at 1. Okay, so you will have a jump. In fact, you will have a jump at 1, but it's not a singularity. It's a bounded function.
Monotone amplitude and sign, which is the sum of sign is bounded.
Yes, yes. That's right. Yeah. So. That's the example. So Nihari theorem tells you that you can always do it. Of course, you cannot do it as neatly and as explicitly as in this example, but Nihari theorem tells you that you can always, so as long as your full operator is bounded, you can always complement. So you can start with an analytic symbol, naively like this, and Nihari theorem tells you that you can always put in the right coefficients here in this part so that the result will be a bounded function.